Recording in progress.
Okay, can people in Cody Hall hear me?
Yes.
Okay, thank you. So, welcome to the first in-person colloquiums in almost 2 years, at least in person for someone who come externally from the university. Paul Abraham, you remember, was the first one to give an in-person colloquium about maybe 8 months ago in and Adam start a new trend, and hopefully soon we'll have more physical meetings. We'll see. I won't hold my breath. So Adam is a real local boy. He actually hailed from Ancaster, we understood it, somewhere near Hamilton. And in fact, a long time ago, I found out that he and my niece were high school classmates. He went to University of Toronto, both as undergraduate and graduate in about 15 years ago. And so he can reminiscent with everyone about how things were a dozen years ago here. He graduated with a PhD working on IR photometry from the CNOT 1 cluster data. But more importantly, when he was a graduate student here, he started the SPARC survey, which at that time was a truly innovative thing to do. He combined Spitzer 3.6 micron data with ground-based Z-band data to use the cluster rest sequence method to find galaxy cluster all the way out to redshift close to 2. And certainly for a long time, this survey produced one of the largest sample, or the largest sample of galaxy cluster bigger than redshift 1. After he got his PhD from Toronto, he went on to a postdoc at Yale, primarily working in Peter van Dokkum's group. He started working on high redshift galaxies and have, I would say, written one of the most important paper on the evolution of galaxy mass function. At that time, that was about 10 years ago, more than 10 years ago. From there, he went on to Leiden for as a postdoc for 3 years, working with Marianne Frank some of the time. And he then moved on to Cambridge as a Calvi research fellow, Calvi fellow, for a couple of years before he finally come back to Canada, to Ontario, to the GTA, to take on a tenure track position at York. And he became associate professor, I think about a year or so ago, got tenure. And he's looking forward to his first sabbatical, which he will spend partly at the University of Toronto. He actually has quite a few collaborators at the U of T, the most significant being the project scientist for GIRMOS, which is a multi-IFU, infrared IFU instrument that Suresh is leading to put on Gemini. Plus, he also collaborate with myself, also with Bob Abraham on JWST GTO programs. So I think he has a lot of connection to this area and have done some really exciting science at high redshift galaxy cluster and high redshift galaxies themselves. So without further ado, I will let Adam to tell us about resolving galaxy formation, spatially that is, galaxy formation at a high redshift and see what that would teach us about galaxy evolution. Adam?
Yeah, thank you so much, Howard. A very kind introduction, and just to tell you guys, Howard was the greatest PhD advisor you could ever have. Absolutely fabulous, and I wouldn't be standing here if it wasn't for all his training. And it's great to be back. So I'm going to tell you, let's see. So we're not getting any feedback, so I can just go, right? So I'm going to tell you, yeah, I kind of have a play on words here, resolving to resolve or resolve issues in galaxy formation with resolved data. So what I'm going to try to tell you today is that we've learned a lot about galaxies, but what we really need to do is start really resolving these things at high redshift to learn more. Howard kind of, I hope this thing works, said this already. Let's see. It was working, I did it. I'm just happy this screw up is not on us.
Is it because we click off of this screen to use it something related?
Okay.
Oh, there we go.
Well, I pressed the button. Maybe I'll stand over here. Can I do that? So, well, yeah, this thing, oh, now it goes, oh, now it works. Hey, there you go. Okay, so Howard said this, I just want to remind you, I'm going to tell you about galaxies, but also one of my PCs for this talk is I love U of T. I love this place. Okay, it's a great place. There I am, look at me, getting my undergraduate degree. Oh my God, 20 years ago, look at, I got hair. There's no gray hair. The sun is shining in my eyes. Here I am getting my PhD, right, all here. So I love this place. And I will show you that not only do I love this place, I love all the people working here, and I'll thread that through my talk. So what are we trying to do? Galaxies are beautiful, right? We look at pictures of them forever. It never gets boring, right? They're the spectacular building blocks of the universe. And what myself, people in this room, so many people in astrophysics are trying to do is really understand where these things come from, right? There's a huge amount of complexity. It is almost overwhelming, right? You look at an image like this, you see stars, you see gas, you know there's dark matter, there's dust, so much radiative transfer going on. Up in the upper right is some Taurus A, big AGN interacting with the CGM mergers. I mean, it's complex, okay? But I'm going to make the argument that we made a lot of progress here, okay? And what we're really trying to find out, the big overarching question in my own work and so many people's work is, how do these beautiful structures grow out of the initial perturbations of the matter field, right? There's the microwave background, the last scattering surface, right? Tiny little inhomogeneities. Somehow, 14-ish billion years later, turn into these grand, beautiful structures, right? Some sort of magic happens here, gravity and a few other things. And, how is the big question? I will argue that we have a lot of work to do on how. How is hard. But one thing we've really achieved in the last 10 years or so is when. We nailed this pretty good, okay? When galaxies form, not so bad. So observationally, we've made a lot of progress. This is the star formation rate density plot. So y-axis is the amount of star formation in the universe versus redshift. And you can see when you integrate over all the star formation in the universe, it ramps up over time. There's a magic redshift in the universe called 2. The universe knows what happens at redshift 2 that we don't. Star formation shuts off and starts to decline, right? I kind of love this plot because everything in astronomy is power laws and scale free. Here's a plot that actually has a time that matters, and I don't really know why. Well, I have some guesses, but so do others. The other thing we've measured is, and this is a shameless plug for my paper, but there's actually not a better compilation of this. So this is the integral of this. This is the stellar mass density. So it's not actually the integral of this. This is actual measurements of the stellar mass, okay, over cosmic time, going out to pretty high redshift. And what you see is stellar mass, well, this is going backwards, but falls off as basically 1 plus z to 2.5, 3. Okay, so this is how mass is growing in the universe. We know when the stars form. We know when the mass is there. At high redshift, the error bars are big. There's not a lot of points, but this is what James Webb is going to do, right? James Webb is just going to completely clobber this. I will fill this in, not me personally, but we will fill this in very, very well in the next few years, which is great. We know when stars form. That's integrated over all galaxies, okay? But what about individual galaxies? When do they form their stars? Well, we can reconstruct galaxy star formation histories. This is a beautiful paper by Daniel Thomas from a few years ago, where he used spectra to figure out when galaxies had their peak, well, just their whole star formation history, basically. And if you divide this up, high mass galaxies are here, Low mass galaxies are here. The Milky Way is kind of in here. What you find out, okay, is a couple things. Massive galaxies form their stars earlier and in shorter bursts, okay? Lower mass galaxies like our Milky Way, their star formation peaks later in the history of the universe, okay? And it's a much more extended star formation history. So not only do we know, when the stars form in all galaxies, we know when they form in individual galaxies, actually not so bad. And a little plug here for my former graduate student, Allison Hill. Here she is, she worked with Marion and myself in Leiden. You know she was in Leiden, as you can see the window, right? That's how you know where you are. You wake up in the morning, where am I? There's windmills, I'm in the Netherlands. This is a very busy plot, but what I want you to look at here is just the right-hand side. And what this is we use some abundance matching techniques based on stuff we did with Peter Baruzzi a few years back on the left, which you don't have to pay attention to, but this is actually the mass growth of galaxies measured empirically, okay, from look-back studies. And what you see is very similar to what was inferred from Daniel Thomas. You see massive galaxies really increase their mass rapidly and then it falls off, whereas lower mass galaxies, it's a much more smooth growth history, okay? And it's largely consistent with this, but remember, these are completely different measurements, right? This is taking spectra and fitting stellar populations on the left, whereas on the right, we really counted up the abundance of galaxies of high redshift and connected them over time. But this kind of thing is largely the same, all right? So, we kind of understand when the stars are forming the galaxies. And, I'm an observer, so I'm biased to observations, but simulations have been doing just as well. It's been a golden era for galaxy simulations. So I'm going to run a simulation here. This is from the Illustris TNG simulation. This is a look at a galaxy like our Milky Way. I'll let it run in a second. It's a really busy slide. What you'll see at the bottom left is the mass of the galaxy growing over time. Top right will be redshift, and bottom right will be the stellar distribution. So here it goes. Boom. You look at the bottom left, watch its mass building up real fast, right? This is a high redshift, like redshift 5. And what you see is just tons of gas accretion, also a fair number of mergers, right? The early history of a galaxy like the Milky Way is really chaotic, tons and tons of gas accretion, lots of little mergers, and this mass really, if you look at this in a very short period of time, this increased by almost 2 orders of magnitude, right? This thing really, really picked up speed. And as you watch it, we're getting into redshift 2. This is still pretty early times for the Milky Way. You can see in the bottom right, it still doesn't really yet look like the Milky Way. Its star formation is increasing over time, which is something we know. There's something called the star formation main sequence. As galaxies grow in mass, they grow in star formation. So we're still in a growth period for this thing. And right around redshift 1 here, and it's going to pause. This is going to show you the gas phase metallicity in a second. So it's metallicity on the left. Halo is metal poor. Disk is metal rich. Rotate around, starting to look like a spiral galaxy. And, off we go. Simulation recommences. But at this point, things are not quite as chaotic, right? The mass growth, if you look at the bottom left, is a lot slower. In a logarithmic sense, the star formation rate is actually a bit higher. And it kind of looks like a normal disk galaxy, looks like the Milky Way basically already by redshift 1. Pretty impressive, right? For the young people sitting in the audience, you might say, well, yeah, great. But if you're older like me, maybe the esteemed Professor Abraham here in the front row, you know that this is not what galaxy simulations looked like 20 years ago. Nothing like this, right? You'd set these things going and they'd make a little nugget of stars that look nothing like the Milky Way. So simulations have come a very, very, very long way. And here's some Milky Way analogs from recent simulations, Eagle, Fire 2, and Illustris. This is their sort of all self-promoted Milky Way galaxies, and they look different, and they do things differently, but they all kind of look like the Milky Way. Pretty good, and this is unfortunately the Illustris plots are not so beautiful, but these are some scaling relations. This is the classic black hole mass versus galaxy stellar mass. The dots are data, the solid line is the simulation. Looks good. Simulation puts the right black holes in the galaxies. If you look at the size-mass relation, so this is size of galaxies versus mass, dots are data, line is simulation. Looks good, right? I mean, I don't know, man. We're making realistic-looking galaxies in these simulations. So not only are the galaxies looking good, I mean, the simulations get the cosmic star formation history pretty good as well, right? Right-hand side, you've seen Left-hand side, this is from Illustris. The simulation is the lines. The dots are some of these points over here. You know, to astronomical precision, it sort of passes through the data. And so you look at all of this and you say, okay, man, I don't know. We measured the cosmic star formation history, you know, observationally, we measured star formation histories. Simulations can make galaxies that look real. They can reproduce the cosmic star formation history. I mean, are we done? Can I end my talk, right, and just go home? It's solved, right? This is a kind of a joke in my thing, right? Is this already a solved problem? And I would argue to you, no, we know a lot. This is a great example of why things aren't solved. So this is a project called the Agora project. And what these guys did is they took most of the most famous codes that are used in galaxy simulations. They gave them the same initial conditions, and then they said, make a galaxy. And they all kind of did, right? Some of these you might know better. Gadget was Eagle. Gizmo is the fire simulations. Doesn't show up so well on the screen. Maybe for the people at home, they can see better. You know, it all makes the galaxy down here. This is the stars at the bottom. But man, the satellites look different. The galaxies look different. This is the gas temperature in the middle. That's pretty different. And so if you think about it, what is this telling you? It's telling you that, you know, you run these big simulations with some physics. We can kind of broadly reproduce what galaxies look like. But, you know, in principle, if they were all doing the same physics, they'd all make the same galaxy, and they don't. Okay, so let's face it, somebody's got to be wrong, right? At least 1, 2, 3, 4, 5, 6 of these have to be wrong, and maybe even 7 are wrong, or at least incomplete in terms of their physics. Okay, so really, although we have all these broad strokes pictures of galaxies, we have a lot of details to fill in. And this just shows you that this is a mass growth history. Remember I showed you Alice and Bill stuff? This is from the simulations. This is the same galaxy, and it kind of grows the same, but you can see it ends up, you know, factor of 5 different mass, and when they first appears, it's also about a factor of 5 different. So, you know, individual galaxies do not have the same growth histories, you know, even given the same initial conditions, which is a bit worrisome. Okay, so how to get better, right? We want to improve on this. What's outstanding? Well, how are galaxies actually grow, right? Where is the star formation? What is the role of mergers? Are galaxies growing from the inside out, outside in? And why do galaxies have morphologies the way they do? And I think these simulations might struggle to tell you those things. Why do galaxies stop forming stars? That's a huge question. I'm not going to touch on much of that in this talk. How important is environment? I'll talk a little bit about that. There's a lot of stuff we need to figure out, okay? And the argument I'm making to you here is measuring better stellar mass densities or measuring better stellar mass functions isn't going to solve these questions, right? We got to do something else. So the argument I'm making is for the next decade, we have to do resolved observations of high-rich galaxies. Okay, we can't just count how many galaxies there are as a function of mass. And so for fun, I went and looked up the dictionary definition of the word resolved. You can do this on your Apple as well, right? It's a dictionary thing. Turns out this applies ubiquitously for the whole thing, right? Because to resolve is to settle or find a solution to something. So definitely we want to resolve this. It also means to decide firmly on a course of action. So, damn it, I'm firmly wanting to solve this problem, unresolved. Apparently in chemistry, to resolve something is to separate it or cause it to be separated into its constituent parts. Definitely, if we want to understand galaxies, we're going to have to resolve them into their parts. And then for all of us astronomers, we know, of course, that to resolve something or see it at a distance, which I thought this was a cool definition, it can turn into a different form and see more clearly. That's not what I thought they were going to write. I don't know what it could turn into. Maybe it'll turn into an apple. And then the 5th one I added is, you can resolve something, which, maybe we already solved this problem, but let's do it again, right? So it's all about resolve. All right, so why is this so hard? It doesn't show up so good on the screen, but this kind of tries to give you an idea of why this is so hard. Top is a couple of random redshift 1 galaxies from Cosmos. Ground-based, really good ground-based seeing, right? 0.6 arc seconds. Wow, and the optical, what do you see? Fluff, right? And unfortunately, the projector's not so good here, but this is space-based of the same galaxies. And if the projector was a little better, you'd actually see bulges and disks and little star formations. So, it's really hard to deal with this. We need space-based. And so if we want to map galaxies, which is what I'm arguing we want to do, Okay, we want to map fundamental properties like their mass and their star formation rate, but in 2 dimensions. What do we need? Well, if we want to map mass, we need high angular resolution and multi-wavelength imaging. That's the key, right? Because the way we get galaxy masses is we fit multi-wavelength data to stellar population models. Okay, and how do we do that? Well, so far, really the only option has been Hubble. Okay, but there's actually, for those of you who don't work on galaxies, surprisingly few parts of the sky that Hubble's looked at that you can actually do this. It's stunning how little there is. JWST is going to help here, but I'll show you later that it might not do as much as we hope. In terms of mapping star formation, there, instead of multi-wavelength data, really what we want is spectra, because one of the best ways to measure star formation is emission lines, things like H alpha, etc. So how have we done this so far? Well, the Hubble grism has done really well, and there has been some AO stuff. And JWST is going to do an awesome job of this, but I'll also make the case that ground-based AO in the IR is going to really completely change how we map out star formation. So let's start with stellar masses, okay? People have done this before. So one of the few places you can actually map out the mass in galaxies at high redshift is this field called Good South, right? For people who don't work on galaxies, you're like, sounds random, it kind of is. But it's a place where there's 7 filters of HST imaging, okay? And this was a paper from Weitz et al. From almost 10 years ago where they actually mapped this out. There's a lot on this plot, but all you want to look at here is the left-hand side. Here's what the galaxies look like in color images. Kind of spiral looking, but kind of lumpy and clumpy and ugly. But if you run all this through stellar population models and make a map of where the actual mass is, that's on the far right over here. And you can see that it's actually very smooth, right? And this has been one of the main conclusions, and I'll show you this a few times as we go through the talk, that although galaxies are very smooth in their mass, but they're very clumpy in their star formation. Just kind of weird, because you would think, well, if stars are forming in all of these clumps, how do I end up with such an overall smooth distribution of mass, right? And there's explanations, but I'll talk about them in a bit. Okay, so that was the Goods fields. Here's a great place to do this. The Hubble frontier fields are a few years old now. This is something we've been working on. Absolutely spectacular data, right? As I said, there's very, very few fields with Hubble imaging and multiple filters. The frontier fields are 1. They're about the equivalent of 12 Hubble ultra deep fields, and they all have 7 to 14 filter images. So this is kind of right. It's kind of right for playing this game, and they're perfect for doing this, right? So they're much, much deeper data than what I showed you before, and they have all of them more filters. So this is work that's been done with Vivian Tan, who's a PhD student in my group at York. And this is a paper we submitted, which I'll talk about, but there's Vivian up in the right corner. And there's a little U of T symbol there because Vivian did her undergraduate here with you guys at U of T, right? And you're going to see this throughout the talk. Many connections between York and U of T. Some of you maybe even remember Vivian from a few years back. And so what she did is she went through this process of creating stellar mass maps, kind of like the stuff I showed you before. You start with an image, you break it up into a little bit of little bins. This is really just to homogenize the signal to noise. Not too, I won't say too much about that. You make a map of the mass. We then scale it back. These Voronoi bins mess up your resolution. So we get the resolution back. We add a little bit of noise and we gal fit. And ultimately we can extract things like Sirsic index, half mass radius, quantitative morphology parameters, but this time actually on the mass of the galaxy, not the light, which is something that has rarely been done before, simply because there aren't very many fields where you can do this. So just to remind you what's going on, every single pixel in the image is being fit to a stellar population model. Okay, so these are just flux versus wavelength. Each box is a pixel, and you can see many of the pixels are the same. Right, galaxy populations don't go crazy from pixel to pixel, but that's what you're looking at here. Every single pixel in that image has been fit to the stellar population model. Okay, so what do you find? So what Vivian worked on in this first paper is she was looking at the properties of cluster versus field galaxies, looking at some of the classic scaling relations, but in their stellar mass, not in their light. So this is the size of galaxies versus their mass, and their Sirsic index versus their mass. Cluster galaxies on the left, field galaxies on the right. Galaxies that are quiescent in red, galaxies that are star forming in blue. And she gets back many of the classic scaling relations we know. More massive galaxies are bigger, more massive galaxies have higher Sirsic indices, which make them more bulge-like. One of the interesting things we noticed is as you get down to these very low masses, there's not such a big difference between star forming and gas-ing galaxies. And there's a lot of sophisticated analysis, which I'm not going to talk about here, matching things up. But what she finds when she does this, okay, is if you plot the fraction of galaxies that are quenched versus their mass, and you separate it into quenched galaxies that are bulge-like versus disk-like, it actually crosses over, which is not something we expected, okay? People have told us for many years that when environment quenches galaxies, like in clusters, it does so independently of mass. And if that was the case, we would therefore expect, the ratio of these two things to be equal. And in fact, they're not, which has really confused us and tells us that the way environment quenches galaxies, it preferentially quenches disk galaxies at low masses compared to disk galaxies at high masses. There's a weird mass effect in there that we don't understand. Okay. So moving on though, we want to do something. That was the first paper of Vivian's. Now in her second paper, we're trying to understand more broad than just cluster galaxies. How do galaxies like our own Milky Way grow over cosmic time? And so this is from a paper from a few years ago by Shannon Patel, and I was part of that. There was also a paper by Peter van Dockum around the same time. And what both of those papers did is they did abundance matching to try to connect galaxies like our Milky Way. And so here's some pictures of them. Low redshift at the top, redshift about 1.3 on the bottom. And this is really an evolutionary sequence, right? As you move up along the columns, this is kind of how we think our Milky Way might grow over cosmic time. And if you do that quantitatively, that's on the right, you can see how Sirsic index changes. So these galaxies go from being more disk-dominated to more bulge-dominated over time, which maybe for people who work on the Milky Way go, well, that seems weird to me, because I thought the bulge grew first and the disk came later, not the other way around, but that's what the data is telling us. And they also grow in size by about a factor of 2. But all of this is based on just how galaxies look in one filter, right? This is in black and white. This is just what they look like in one filter. And the rest wavelength of that filter is very different here, than it is here. And so what Vivian's working on is actually doing this in mass and pulling out how these galaxies grow in mass. And this kind of just shows you here's her galaxies. These are supposed to be progenitors and descendants of the Milky Way. So this is mass versus redshift. So, they're kind of Milky Way mass nearby and they get smaller. We run into galaxies at high redshift. I'll talk about that in a second. And here's just some examples of what she gets. And yeah, maybe the people at home are seeing better than on here, but here's a galaxy color image. Here's what it looks like in the ultraviolet. Here's what it looks like in F160. But here's the mass map, okay? And one thing that we'll see better at home is that this mass map is more concentrated than this light map, okay? And if I show you another one, the same thing, right? Here's a galaxy, it's quite clumpy actually, right? It's very clumpy in the ultraviolet. Kind of has a fluffy F160 image and a very, very sharp stellar mass map in stars. Okay, and so unfortunately, we didn't quite get to the fit. I'm sorry to leave you kind of hanging, but you can see what the answer is going to be that, this growth that I showed you here, where Sirsic index increases over time, which is kind of, I think, backwards for how we think the Milky Way grows, is probably just an artifact of using light. And when we use mass, this looks much more bulge-dominated at high redshift, which actually fits things, okay? And so that's ultimately where we're going with this, which I think is going to be cool, right? So yeah. These Milky Way progenitors in mass, they look very smooth in mass, but they're clumpy in star formation rate. There's also a lot of growth out here, but the frontier fields are not deep enough, okay? And what's really going to kick butt on this is our big GTO program, CANUCS. And this is a program that was given to Canada on behalf of providing the NEARIS and the Fine Guidance Center for James Webb. It's a 200-hour program. It's PI'd by Chris Willett, and you can see here, it's a great collaboration between people here at U of T. There's Bob, Kartik, and Lamia, and at York, myself, and Ghassan Saru. And CANUCS is going to be absolutely fabulous for mapping out the stellar mass of galaxies like that. One of the reasons is, I'll talk about the spectroscopy we'll do with CANUCS in a little bit, but in parallel to doing spectroscopy, we're doing a 14 medium band survey in 5 fields. And these are all the filters we're doing, okay? Spanning from where Hubble looks pretty much out here in the optical, all the way up to 5 microns. So if you think about what Vivian was doing there with the frontier fields, right, with only 7 to 14 filters, we're going to do even better. It's going to be deeper. James Webb has more angular resolution, okay, and you're going to have more filters. All right, it's going to allow us to take this growth and mapping of galaxies to a very, very high ratio, which is exciting. Okay. So JWST is going to be fantastic for this. Oops. Right? No, I probably did that. So, oops, there we fixed it. So JWST is going to be fantastic for this. We're going to have higher resolution, longer wavelength, go to higher redshift, but we really could use more area, right? Like goods, we can do this for a small number of galaxies, the frontier fields, you know, as well. But James Webb does not have a huge field of view, right? It's only slightly bigger than Hubble, which means that, you know, we've had Hubble for all these years. We're not going to get tons more area with James Webb, even though we're going to get beautiful data. So we want more area, and, you know, more filters would be good. I mean, I told you we're going to do 14 filters with James Webb, but I'd still like to have more. So what's my perfect survey? Well, my perfect survey, instead of covering hundreds of square arc minutes, is going to cover square degrees. We're going to have like 20,000 galaxies, and we're going to have tons of filters, right? And you will say, well, it's great, you know, and I want a Ferrari for Christmas, and I'm not getting it, and you're not getting it, right? Because how are you going to do this? Well, I'll show you there's a way to maybe cheat. So, you know, there are some surveys we can exploit. Here's the Cosmos field over here on the right. Here's some of these Hubble fields on the left that we've used. Cosmos would rule, right? Cosmos is 2 square degrees, it's big, okay? And there's more than 30 filters. In fact, there's almost 50 filters in Cosmos. So, okay, it'd be like 2 out of your 3 boxes are checked. Uh-oh. Cosmos is ground-based imaging, and I showed you how currently ground-based imaging is. We can't do this, right? You can't, you know, well, you can't see it on the screen, but, you know, that's what kind of maps you make with HST. This is what you do with ground-based. Well, we've been cheating on our exams because we're trying this new idea, which is this algorithm called finite resolution deconvolution. And what it is, and people have known about deconvolution for a long time, but I'll show you that there's some cool upgrades that people have worked on. So what's going on with ground-based imaging is you have a star, photons come into the atmosphere, they get the turbulent medium, you know, they get moved around, and what you end up is a blurred star. It's called the point spread function, right? In principle, if you know the point spread function well enough, you can take it out, in principle, right? In principle, you can fix this. In fact, that's what AO instruments do, right? They measure the PSF, very high efficiency, and they adjust the deformable mirror. But maybe we can post-process this. But in practice, it never works very well, all right? And the reason it does is background noise is a real problem, right? Most deconvolution algorithms that try to take out PSFs can't tell your galaxy from background noise. So you know what they do? They deconvolve your background noise, right? And make all sorts of beautiful structures in your noise, which are very, very hard to make measurements on. Also, we tend to deconvolve to the best resolution we can, and that creates all sorts of weird high frequency effects because there's sampling theorem going into this. So it tends to be that this just really makes a mess of your data. However, some groups have been working on improvements to this, and this group here, led by Cantale, has worked on this thing called finite resolution deconvolution. What is this? So the idea is, let's not deconvolve to infinite resolution. Let's only do a finite resolution that's maybe a few times better than your ground-based, okay? That gets rid of most of the high frequency noise because we're not trying to get the high spatial scales. And there's a beautiful new algorithm built into it that uses a cost function where we really try to separate the noise from the signal and not deconvolve the background noise, only deconvolve the signal. And when you put these two things together, you actually get something pretty cool. So this is work by Vishal Sok, who's a graduate student, a PhD student in my group. There's also a U of T banner beside Vishal. You know why? Vishal also went to U of T for his undergraduate. I take all your best people. But I take some good people from you, right? And so here's Vishal's work. This is a paper that was published this year. Also, Leo Alcorn, who's a postdoc here, part of my group, worked on this paper as well. What are you looking at? There's a part of Cosmos that has Hubble imaging in multiple filters. So along the rows are 4 different galaxies. Over here is V-band imaging. The left side is the actual ground-based data. The middle is Vishal's deconvolution. Here is the HST image, okay? And you can see a lot of the features look the same. It unfortunately really doesn't show up well on this projector. But in general, when you look at the color images over here, things look pretty good. If I zoom in, right, there's the ground based on the left. It's kind of just a blobby thing. Here you start to see structure, you see a bulge, you see a disk, very similar stuff that you see in Hubble. It's not perfect, but it's free. I don't need a space telescope, okay? So we did this. Wiesel deconvolved 20,000 galaxies in 15 filters in Cosmos. Don't look at the left side. This is all the funny stuff. And what we did is we used it to study how clumpy star formation is in galaxies. So let me move this over here. This is the fraction of galaxies that have clumpy star formation versus redshift. The top is low mass galaxies. The bottom is high mass galaxies. Wiesel's measurements are the colored points. And what do you see? Well, you see galaxies get more clumpy over cosmic time. Okay, the other thing you see is the open circles here, or the squares, those are Hubble Space Telescope measurements. Guess what? Fully consistent with our deconvolved data, right? In fact, we have much better error bars because most of these studies have about 100 to 1,000 galaxies, and we have 20,000, okay? Pretty impressive. And so what we find is the clumpy fraction of galaxies increases significantly with redshift. Lower mass galaxies have clumpier star formation. This amplitude here is higher than this amplitude here. You probably can't see it that well, but it's true. And our error bars are almost zero in terms of statistics when we compare to other studies, right? We've got twice as many points, and you almost can't see the error bars. And that's the power of deconvolving ground-based data. And I think this is an exciting thing we can do, right? This is just the beginning. There's a lot more we can do. One thing Wiesel is moving on to is just measuring the mass growth of galaxies. That was how clumpy star formation is, but we can also make mass maps. And so here's a mass map of one of these galaxies. And what we've done here is, this is an average mass map. So this is the mass density of galaxies on the y-axis versus the radius for massive galaxies in sort of the intermediate redshift universe. All right, and Wiesel's deconvolved data is the points, and the solid line is a fit to them, and the red is a measurement from Van Dokkum. Okay, and so although it's somewhat consistent with what Van Dokkum found, there's a lot less mass at large radius. And one of the differences, Van Dokkum just used one filter, and he assumed that light traces mass. That's not what Wiesel did. Every pixel in this image was fit to a stellar population. This is actually mass. And when you do that, you find out these galaxies actually have a lot less mass at large radius, which maybe was kind of obvious because galaxies have color gradients, which we have ignored. And what that means is we've already been really surprised at how much size growth there is in massive galaxies. I think we've underestimated it, okay? 15 years ago, we were explaining that galaxies were growing by a factor of 10 in size since redshift 2. But we've been underestimating their sizes. Perhaps galaxies are growing by a factor of 30 to 50 in size since redshift 2, when we actually measure their mass profiles correctly, right? So this is work in prep. I don't have exactly the number yet, but I will get it. But I think it's really exciting. So there's a huge future for this, right? Because Euclid is coming, 15,000 square degrees in the infrared. But in the optical, nothing. But we are doing this big CFIS survey from the ground. And of course, complementing all of this is going to be LSST, which is going to have 70% of the night sky. So you've got beautiful space-based infrared, but your ground-based optical, well, not as good. But I think this is where deconvolution could be really cool, right? Instead of 20,000 galaxies, you can imagine, 20 million galaxies, 20 billion galaxies, maybe if you use LSST. There's a huge future in this. Okay. How much time we got? I got about 10 minutes. Yeah, okay. So that's stellar mass. Let's talk about star formation, right? That's how ways we can map stellar mass, James Webb, image deconvolution. Okay. So one of the ways we've been mapping star formation in recent years is with the grism on the WIF3 camera on Hubble. And how this works is this is slitless spectroscopy. And the way it works is it's almost like taking an image of a galaxy at every wavelength. So light comes in the camera, you disperse it, but there's no slit, okay? So what you're getting is, this is like a galaxy here, it looks like this galaxy. This is its one-dimensional spectrum, right? It's a nice emission line here, this is H alpha. And you can see it, right? As soon as you hit the H alpha line, there's like an excess here. And so what we typically do to get a map of the galaxy in H alpha is we take the continuum here, we take it in 2 dimensions, and we subtract it from the line. And when you subtract it, you end up with a map of the galaxy in HL, which is effectively star formation. Eric and Nelson did some fabulous work back at Yale a few years ago doing this with the 3D HST survey. And this was the main result, and you see this pulled a lot. This is the size of galaxies versus their mass. Blue is their H alpha size. Black is the size they are in stellar continuum. And so the big result here was the extent of star formation in galaxies at redshift 1 is bigger, okay, than the disk of stars, basically. So galaxies have been smaller in the past, and they're growing bigger now. Well, that's redshift 1, okay? So, and this has led to the idea that galaxies grow inside out, right? The inside is already there, the outside is still growing. Okay, so we did some work on this. This is the PhD work of my former student, Jasleen Matheru. When I was a postdoc at Cambridge, they allowed us senior fellows to have PhD students, which I don't know why they did that, but I was very fortunate. So 2 years ago, as a York professor, I graduated a Cambridge PhD. I don't know how that happened, but it did. Here's Jasleen. This is a picture from last week. She's very excited because she was offered the Dawn Fellowship at the Dawn Center in Copenhagen, which is exactly the job she wanted. So she's very, very pleased, and she's very well deserved. And so she wrote a series of papers for her thesis. I'm only going to talk about one today, but there's lots of exciting stuff about clusters there. And what we did is we observed some redshift 1 clusters, okay, with the grism. And this kind of shows you, here's one of these clusters. This is your beautiful slitless spectroscopy. This was a big program. This was almost 40 orbits. I showed my parents this. I said, Mom and Dad, I got time on the Hubble Space Telescope. And they said, that's amazing. Show us a picture. And I said, look. And they went, what did you do? It's terrible. Is it in focus? Yes. Okay, anyway, what did Jasleen do? So she did the same kind of thing as Eric and Nelson. What are you looking at here? She wanted the stellar continuum, so we got that from the F-140. Here's the galaxies in 3 different ranges of mass, okay? For those of them on the left. Stack them up. There's not a lot of signal in the H alpha, so we stack them up. Here's the actual image. Here's the model, almost no residual. Doesn't show up very well in this projector, but it's true. Here's the H alpha, same thing. Fiddlehead-Sursic model, nice residual. So we have the continuum and we have the H alpha. So what do cluster galaxies look like? Maybe you want to think about it before I show you the answer, right? Are they going to look like field galaxies? We think there's lots of environmental effects in clusters, right? Ground pressure stripping. If you think about these big H alpha disks, if you look at them in the Virgo cluster, they're not there. They get stripped off. They're gone. So our full expectation is that the cluster galaxies are going to be smaller in H alpha than in the continuum. Okay? Wrong. No, sorry. What are you looking at? Left-hand side is Eric and Nelson's work. What I showed you, just we rederived it ourselves. This is size versus mass. The black is the stellar continuum. The blue is the H alpha, right? H alpha is bigger than the stars. The clusters, there's not that many galaxies, but basically, you know, the star, it's about the same as this. If you do the statistics, this is fully consistent with this. The H alpha disks of galaxies and clusters have high redshift, exactly the same as galaxies not in clusters. When we were like, surely we did this wrong, so we redid it for 2 years. We redid this to try to make this go away. We tried everything we could. We could not make this go away. So as far as we can tell, this is real. Okay. But, so what does that mean? How can they have the same size disks as field galaxies? What you're looking at here is, this is the difference in H alpha versus continuum from cluster to field. So cluster and field galaxies are the same. Everything would be here. And you see that, right? Here they are. They're the same. Okay. What Jasleen did is she went and looked at recently quenched galaxies, galaxies that are so-called post-starburst galaxies. So are those different? And the answer is yes. Turns out we can still see these recently quenched galaxies a little bit in H alpha, okay? But they're tiny. They're really, really small. And so what this sets up is it's very consistent with this idea that's been around for a while of a delayed then rapid quenching process. So what happens? Galaxies fall into clusters, right? And they just live their life, right? There's a delay time. They don't care they're in a cluster. Everything's fine. And then all of a sudden, one day, everything is not fine. And they quench very rapidly, and they get very, very small. But for most of the time, they just look like normal galaxies. And this kind of fits with this picture. This is a picture we've been pushing for a while in different ways. Okay, well, this is what we're going to do in spades with CANUCS, all right? CANUCS is primarily a spectroscopic survey. The MURIS instrument is sort of like the WIF3 grism on steroids. We get, not only do we get a couple of filters, we actually get a third filter that has higher spatial resolution, that has higher spectral resolution. We're going to be able to make these maps like nobody's business, okay? And it's going to be a fabulous new era for mapping star formation in these galaxies. So we're really excited to do this work with CANUCS. So HST and JWST are great, but I'm going to tell you that they're not the only way to map star formation in galaxies. In fact, they might not even be best. They might be. It's up for argument because ground-based AO surveys have made huge strides in recent years. And lots has happened. And ground-based AO is very competitive with space-based stuff. Most of this work has come from the Symphony instrument on the VLT. And I'll show you some of those results very quickly. The big survey is got a horrible name. It's called the CZ SIMF survey, which I still don't know why, but that is what it's called. And it's taken them almost 10 years, but they have observed 36 galaxies with laser AO, right? And this gives you a spatial resolution that's actually better than the Hubble grism, okay? It's about 150 parsec resolution. If you 1.5, I made a typo last night. So here it is. This is some of the main results from SIMS. These are the actual pictures of the galaxies in H alpha. This is their star formation rate on the y-axis and their mass on the x-axis. This is a sort of classic star formation rate sequence. But each one of these is actually a picture of these galaxies, right? And they're pretty weird looking, right? Although you do see some commonalities. There's a lot of things that look kind of like, for lack of a better description, donuts, which are probably disks, right? These are galaxies with disks, and then they have a bulge in the middle, so not so much gas in the middle. But one of the things that's really in common is all these dots, right? All these lumps. And you saw that. You saw that in the UV maps I was making. Star formation is very clumpy at high energy. These are knots in H alpha. And so you see the same thing in H alpha as you do in the ultraviolet. But there's a huge diversity here, right? I mean, these things are all a bit different. There are some commonalities, but things over here are not like these, are not like these. The initial results from these 36 galaxies tell you that most galaxies are disk dominated, right? There are some low-order disks. You see it better in the kinematics than you do actually in the morphologies, but you'll take my word for that. And these disks often have large clumps. So 36 galaxies are great, but we need multi-object AO IFU spectroscopy, right? We cannot like do this one galaxy at a time, one galaxy at a night, 10 years to do this. So how do we do this? We do this again with U of T people because I love U of T. We're building this beautiful instrument called GIRMOS, right, which is a multi-object MOAO, so that's multi-object AO. Also does LTAO, does IFU, and there's also an imager, right? Suresh is the PI. I have to tell you, working with Suresh for the last couple of years, you guys did one of the best decisions you made was to hire this guy. This is a guy who's doing an unbelievable job of managing an incredibly complex process. Also, Mason Lamb, one of your Dunlap fellows, doing just absolutely fabulous work, putting this incredibly complex machine together. So what is this thing going to do? Baseline is that we're going to have 4 deployable IFUs over about 2 arc minutes, okay? And those are going to be available in 2 ways. You can either put the IFU anywhere you want and do what's called multi-object AO, which means you optimize the AO for exactly that position, that position, that position, and that position, giving you the best possible AO you can. Or else we can take all 4 IFUs, jam them together in the middle, and have what we call the compact tiled mode, or a super IFU, which we're going to use with laser tomographic AO, okay, giving also very, very high quality correction. We've also added the science grade imager, so if you don't want to do spectroscopy, you can also use GIRMOS to do imaging. So why are we doing this? Well, the science package for GIRMOS is huge, right? We're going to do everything from globular clusters, intermediate mass black holes, transient star formation, nearby galaxies. But of course, you know, the thing I love the most is distant galaxy evolution, right? And I think we're going to have a huge impact with GIRMOS in this. And the other reason we're doing this is really going to be the first science-grade multi-object adaptive optics instrument, right? This is not easy to do. It's never been done before for a science instrument, only test instrument. And this is really what you want to put on the generation 30-meter telescopes, right? You want to use their incredible angular resolution, but you want to do multiple galaxies. And so this is really a pathfinder for doing that as well. So amazing science, and also pathfinding technology. And so one of the things we're going to do is we're going to make maps like this. This is from SIMS. This is the continuum, star formation, effectively metallicity, kinematics. You're going to map everything you want, almost, about galaxies. And because we can do it in multi-object mode, we're not going to map 36 galaxies. We're going to map hundreds of galaxies with Charlie parsec resolution. Okay? And we're also going to be a pathfinder. So that's my talk. That's what we're up to. Things I hope I convinced you of today is I love this place. Right? I love working with you guys. Yeah, thanks, Matt. Home is home. It's good to be home. Mapping galaxies in 2D is the emerging field in galaxy evolution. You're going to see so much of this in the coming times. James Webb is, there it is. My God, I can't believe it's actually there, right? But James Webb is going to be fabulous for mapping the stellar masses of galaxies. Image deconvolution is really exciting, right? We can do this. For mapping star formation, James Webb's grisms are going to be amazing, so is CANUCS. And ultimately, in a few years, we're going to do this with GIRMOS. Even better, it's going to be spectacular. So you got to have me back 5 years from now. I will show you all these beautiful maps. It's going to be fabulous. So thanks for having me. It's been a pleasure.
Thank you, Adam. So we're going to open Adam to questions from the audience. There are two sets of audience here. So for the people on Zoom, please use your hands up sign on Zoom. And I think is Bob, are you in the audience live? And for people in Cody Hall, Bob will call on those who have the hand up. And we sort of take turn between Zoom and between virtual people and real people in the questions.
Do you want to take turns, Howard, or do you want to just?
Or just whoever we have someone, just
Okay.
first come, first serve.
Okay, how about Josh?
Sure.
All right, so I have the standard question here. Paragraph for me, which is so in sort of a lot of work we presented, you're using the image deconvolution algorithm. And my question is why stop at sort of semi-deconvolution? Why not just go to like a full color model? You're going through all this work of doing kind of more of methylation and trying to find deconvolution, kind of limited matching with HST. Why not just try and actually model things at HST resolution and then go for that word, go forward to the actual ground.
I think it's not a bad idea at all. I mean, honestly, yeah. Why not? I don't have the software to do it. So we can, I'm happy to work on such a thing. I agree with you. Forward modeling could be really powerful. I mean, one of the reasons we chose to do this is simply, people have done the hard work for us, which is develop this deconvolution code and do all this kind of stuff. And so for someone like myself, who's not an expert in forward modeling, you take this out of the box, you can do the kind of stuff that we normally do, and you can do this. But I agree with you. If you know the PSF, you don't have to go backwards, you can go forwards, right? There's no reason to have a preferred direction. So I would also be very happy to try that kind of stuff.
Howard, is there a question on Zoom? Because if not, there's another one here.
I don't see any hands. So
All right, well, the question here is from me. Can you go back to the slide right near the beginning where you were showing the predictions from the numerical simulations? Like, there were like 7 in a row.
These?
Slide forward.
These?
What the
Yeah, the Agora project.
Oh, the Agora. Yeah, sure, no problem. That should be there. Yeah.
Right. Okay, so looking at these, you were like, oh man, look at how different they look on the bottom. But I was like, man, look how different they are in the middle.
Yeah, gas temperature is crazy.
Yeah, and so like 2/3 of the baryons are in that middle count.
Yeah,
So you could kind of just go, well, screw it. I'm not even going to care about anything at the bottom.
sure.
If I just understood what was going on in the middle,
Yeah,
that would be where all the action.
I agree. It's harder to observe that stuff, but I mean, you can, but it's hard.
Yeah, it's like Muse cannot do it at dimensions.
Yep,
Like
yep.
Sirius building an instrument that can be.
Yep. No, I agree. I think it's fabulous. I mean, you know, I mean, I'm with you. I mean, this is what it's really about is, you know, mapping this kind of stuff in gas and in stars is the way to discriminate between these models. Because if we do this, you know, you can say, you know, galaxies never look like this, they look more like this, or vice versa, right? And it is really disturbing how different, you know, they all kind of get the right answer en masse, but specifically, they do very, very different things. Which I don't know what that means. That must mean something philosophically, like, you know, there's some sort of mean value to all. But yeah, I mean, I hear you. Mapping gas is a great thing to do. It's tricky to go way out of the halos, but as you say, we can do this in absorption at some level.
Hey, Howard, I think there's a question on Zoom, right?
Okay, Chris.
Yeah, great talk, Adam. A quick question. So about the clumpy distribution of H alpha, those H alpha clumps are more prominent in the high redshift galaxies. Does that mean that the clump luminosity function is extending to higher luminosities, or does it mean that the galaxy overall is just smaller and dimmer relative to the clumps that it has?
Yeah, so that's a great question, Chris. This is like a huge field because one of the things people are, I'm not going to be able to get forward to the slides, but one of the things people have questions have is that as good as the resolution we have at high redshift is, like sub-kiloparsec, it's actually still not that good to resolve individual clumps. And the question is, are these big clumps like actually big single clumps, as you say, or is it just that you have a whole bunch of little clumps that are blurred together into like one super clump and I can't tell them apart? And so there is some preliminary work from galaxies that have been gravitationally lensed. Okay, and and it's only handfuls of galaxies that you can do to get the magnification. But in those handfuls, and they're not the most massive galaxies, but it looks like it really just is a lot of blending. Okay, that there's not like significantly huge numbers of significantly larger molecular clouds. It's just there's so many molecular clouds. But even the lensing only resolves things so well, and you know there's a lot to be done there. And I think you know we'll do a bunch of this with James Webb. But honestly, you probably need like 30-meter telescope kind of angular resolution. You know, 30-meter telescope will give you whatever 5 times James Webb, and that's really where you would solve the problem really, really well.
Great, thanks. I have a quick second question, if that's
Yeah, go ahead.
On the inside-out growth of the galaxy mass distribution, you know, there's lots of constraints on the growth of the Milky Way from stellar archaeology. So how do those two things compare? Is the picture for a Milky Way-like galaxy similar to the picture we're getting from the Milky Way?
So I have to say, you know, yeah, I'm trying to get to the slide here because I want to show you. So in general, you know, no, right? This is kind of what I was arguing is that you think the bulge forms first, but these things look very disk-like, right? And that's what you kind of see in their Cercic index. And then they become more bulge dominated with time. But the Milky Way, right? And there's not a lot of detail on here because people who do the Milky Way don't compute Cercic indices, but you think the bulge forms first and the disk comes later, right? If you do archaeology. And so it's kind of backwards. But, you know, there's two issues. One is the Milky Way is but a single galaxy, and this is averages of many. So maybe there's no problem here. But, you know, the flip side of this, as I was showing you, which is that when you do these kind of measurements in the stellar mass, which you see here in the bottom left, versus light, which was the plot I showed you, the stellar mass is much more compact. And you can see it looks much more bulge-like. And so one way to really reconcile this, you know, issue we have, which is that it kind of looks different than what you might infer from the Milky Way, is by doing this kind of modeling, all right? And unfortunately, yeah, we didn't quite get to the numbers before today's talk. But, you know, hopefully I'll be able to, you know, by the end of the year, we'll publish a paper that looks at this, and it may help reconcile things a little bit more, that, you know, the bulge comes first and that this comes later, when you're more careful about how you map light into masses.
Thanks.
Hey, Josh has got a question here, Hunter.
Okay.
I'll ask a second one as well. This is also totally separate from, so on the cluster comparison, we were looking at sort of the difference size between sort of starburst and then normally traveling galaxies. You discussed sort of this delayed and rapid, this is evidence for some delayed and rapid process. Are there any sort of mechanisms that seem to explain that sort of thing? And could this also be a signal? One thing I'm always cognizant of with galaxy comparisons is sort of this longitudinal effect. We're always looking at populations of galaxies sort of in different environments and not necessarily just matching one particular galaxy's evolutionary growth. Like, is there any, what sort of mechanism can explain that sort of thing where galaxies just kind of sit there at some quench?
Yeah, so the argument we've made, and we did some modeling, and I wrote a paper a while ago on it, is the idea that you need to reach some sort of critical gas density to have ramp pressure be effective enough. So you can imagine, you've got a cluster halo. Remember, these are redshift 1 clusters, so they're not, their intercluster medium is not as well developed. But you fall in, you kind of live on these orbits that, are in the outer part potentially. Okay, and maybe there's a little bit of disruption of what's going on, but not so much. Something perturbs your orbit, you plunge through the center, there you feel a huge amount of ramp pressure. And because, these have very fast dynamical times, right, because they're small halos, well, relatively small halos of high redshift, you get much more of a, snap punching kind of effect. And if you look at punching timescales, they get much longer over the cosmic time. They're very fast at high redshift for clusters, and they get very much longer, which is exactly, they scale basically with the dynamical time. We wrote a paper in 2018 by Ryan Foltz showing that. And so I think that's, at least at the moment, our most plausible, explanations. It's really about orbits and gas densities. And it does seem to work out, but it's not something that's really been done, very carefully, and it's not something that we've looked at really carefully in hydrodynamic simulations. But there are problems like galaxies in clusters in hydrosims. Sure. There's challenges to comparing there. But that's the best explanation we have at the moment. But I'm very happy to change it if that's not the right answer.
Okay, so I have a question myself, Adam. So I always find these grism stuff, whether it's Hubble or I guess even JWST when it comes, seem to be rather complicated to reduce and analyze, and probably not as good as doing direct 2D IFU, which is what GIRMOS is supposed to do. So I understand that GIRMOS science team had developed a few of these high redshift galaxy projects, either with cluster or with few galaxies. I wonder if you can say a few words about how in 5, 6, 7 years when GIRMOS is come online, how that would do much better than what I assume would do much better than what have been done or will be done with JWST.
Yeah, I mean, it's a good question. I think they're both competitive with each other. There are challenges with doing the space-based grism because you have. I didn't show it here. I won't fast forward to the slides. But the problem is, there is a dispersion, right? And so what actually ends up happening is your resolution, your spectral resolution is proportional to the size of your galaxy, which is kind of a pain. You got a big fluffy galaxy, you get crummy spectral resolution, you get a nice nugget, you get beautiful spectral, you get better spectral resolution. Prisms are never beautiful. And so, there's a lot of challenges there that, we have various ways of overcoming and masking certain parts of it. But your point is great, which is that with the IFUs with the AO, that problem goes away. All right, and it's much cleaner. However, for H alpha morphologies, I think James Webb is going to probably clean up. But the thing that the grisms cannot do is they can't do resolved kinematics. Okay, you don't have the spectral resolution to actually look at the motions of the gas. And I barely talked about this at all in this talk, but there's a huge amount of information buried in the galaxy kinematics. And so, even if at some level the James Webb grism eats our lunch on, star formation distributions, it can't do kinematics, and we'll do tons of that with GIRMOS, which I think is going to be really, really exciting. Also, metallicity maps are much easier with GIRMOS than they will be with James Webb. So there's a lot of fertile ground for GIRMOS, and I think these things will work in tandem, basically. Right?
Thank you.
Well, Howard, I think we're running late. Maybe we better say nice things about Adam and go.
Okay.
I
Okay, well,
So you want me to do it?
You already said too many nice things. We should just sign off.
okay, so, well, Adam, thank you very much for dropping into the department.
Yeah.
And, you know, hope this warmer place than up north at York. And for, you know, very exciting talk about, you know, all these future, you know, already done and future upcoming things on resolved observation of high redshift galaxies. And there are no more questions. Unfortunately, you know, we're still not in a stage where we can go to the lounge and have coffee and talk. So
I will talk to you all in 10 months when I'm on sabbatical here. It'll be fun.
that's right. So Adam's going to be here beginning of 2023, I believe. And so he'll be around, and hopefully by then, everybody will show up for real colloquium and real coffee, etc. Okay, so thanks, Adam.
Thanks.
And thank everybody for taking the time to come.
All right, I'm gonna log off.